Bismillahirrahmanirrahim. Okay, this is the continuous subtopic under our module 6. So last time we have video related to our module 6, but this like cover on our adder, comparator, decoder. What else? I've got already. Now we're going to look into another subtopic, which is encoder. So in this video we're going to cover all until module 6 finish, and I think it's not too long. As long as you already knew previously about the basic full adder, encoder, decoder, and etc., it's might easy for you to understand our next subtopic. Okay, so let's take a look into encoder. What is the difference between just now in the previous video we learned on decoder? So what is the difference? So the biggest differentiation between decoder and encoder, D and N, is decoder you have fewer or less input, but you have many output. That thing is much more easier for you to like when you look into the picture, then you know, okay, if you compare to the input and output, for decoder, output is many and input is fewer, while for the encoder you can see there is many input compared to the output. So it's going to be like vice versa. Here, let's say you have 3 and this is to the power of n, this will be 3 and it will be 8 to 3. Just now for decoder you have 3 to 8 and another one 4 to 16, isn't it? So for decoder, encoder, you're going to have a vice versa like this. Okay, you can go through and read all of this. Encoder does the opposite things what decoder did. Last time you convert the binary or BCD code to decimal. Now you having the decimal, you're going to convert to the BCD. That is only big differentiation between each other, and the rest the extra things you can go through it. Let's take a look on the keywords, that important things. Type of encoder, you're going to have 2. Last time for decoder you have 3, and for encoder you have decimal to binary encoder and also parity encoder. So let's take a look one by one. We have here in 8 input decimal and 4 output binary. 10 to 4 line encoder. You're going to convert your decimal value to your BCD code. So all of here is your the colorations of your decimals, and here will be your BCD code. This is decimals and this is BCD code. Let's take a look how basically the decimals look like. So similar, if you have over here your BDC equal to 0, of course you're going to have like 0, 0, 0, 0, 1. If let's say here is sorry, means that 0, this one is higher. I mean, it's 0, 0, 0. If the rest will be 0, 0, right? So if here is 1, which is turned on, then it will be 0, 0, 0, 1. The rest will be 0, 0. Okay, let's take a look in the table, through tables. That is much easier for you to understand. Here you can see high input for SO, which is the switch S0. Then your output will be, this one is 0. So if you convert to the binary, you're going to get 0, 0, 0, 0, 0. See there? And you have a high at the S1 here, like this. The rest, of course, it will be 0. You're going to have 0, 0, 0, 0, 1. Convert 1 to binary, you convert 2 to binary, you convert 3 to the binary, you convert 7 to the binary, you convert 8 to binary, and you convert 9 to binary. All together is 10. The rest will be invalid. You try to remember and recall back, but BCD is having an invalid if there is several inputs, right? So please make sure you refer back to your numbering system. Okay, now from the truth table there, you can see if high at the 1 3 5 7 high, A high if, okay, A high if, let's say you have like 1 3 7 9, 1 is high if blah 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 blah. But this thing, if you can remember, is okay, but the understanding of this, which is when you have here is decimal, this is binary, you just convert, okay. Therefore, from all of this, from your truth table, you can draw your circuit like this. Okay, when you have here when you have output of 0 is 1, what input you have? 1 1 1 1 1 here for the output of 0. So what is your input value? Here will be your 0 1 0 0 0 0. So S1 will be 1. So these things you're going to have the like your Boolean expression, so you can come out with the circuit. Try to draw your own circuit from this truth table. Okay, exercise 6.6. Suppose high are applied to input 2 and 9 of the circuit. What are the stage of the output line? Does this represent a valid BCD code? What is the descriptions on the encoder logic? Okay, you have both, okay, and here. So your input number 2 and input number 9 is going to be high. The rest is 0. Is it available here in the truth table? You can see. Okay, in here you can try to put in the value. Let's say 0 1 0 0 0 0 0 0 1. Okay, try in your DIT simulator, draw this circuit, or maybe you can just easily get the value. Can you get the output? Let's say I do this one. Okay, 0. Here is 0. Here is 0. Here is 0. Another one is 1. So it will be 1 over here. This 0, this 1, it will be 1. As long as you have at least 1, then you can have 1, isn't it? This 0 0 0 0, is it? I hope that is correct. And lastly is 1 and 0 is having 0. So you're going to have like this. But is it BCD code for this one valid or not? Then you need to check your module 2 back. What is the resistance on the decoder encoder logic? So let's take a look. What is it? What is the output? Okay, just now is input 2. Okay, 0 1 0 0 0 0 0 0 0 0. So what is your output for input 9? What is the output for A, B, C? So it is come out like this. And does it represent a valid BCD code? Yes, this valid BCD code is between 0 and 9. Okay, this one, do it one by one. Okay, do it one by one. When you have input 2 and when you have input 9. Okay, that's why it's valid. If just now what I did, it is supposedly invalid because you have two high input. Number 3, only one input can be high. See this one, the rest must be low. So just now when I having two input together, this might be confused. Suppose I apply to input 2 and here, if you have the same time you have two input, then going to have invalid because you need to have encoder one time, one only input need to be high. Okay, next is our encoder for parity encoder. Just now is your decimal to BCD. This one is parity encoder. So what is the parity things? Dalam mathematical, in the mathematical, you're going to have like factorials, multiply and division, subtraction and additions. It's flow into the parity. So this is the number one parity. But priority for the encoder, which one will be your priority? Okay, produce BCD code corresponding to the high decimal value at the input and ignore the low value. See this one. So you're going to pick much higher. If pin 9 and 5 low at the same time, only pin 9 will be recognized because it has higher parity because of this. Okay, highest value input has parity. The input will be okay. This one is why it's low. Let me show you. This is no bubble thing. So you can see it is active high. Now you can see here bubble there. That's why in this example of your parity encoder, it is mentioned about low. Just now it is having a high. Okay, high is active high. So if let's say in this question you're going to apply this one 9 because this 9 is 1 and it is parity. But here we are looking at the parity encoder. For this encoder, active low encoder, because you have bubble here things you can see. Okay, now we compare 9 and 5. Which one is higher? This is higher. So you're going to ignore your 5. Only pin 9 will be recognized with the 0 input. The rest will be 1. Why? Because this is active low. The output will be 9 apa ya? 9. 9 will be 0, 1, 1, 0, 4, 9 because active low at the output. 9 will be this one. Active low at this okay. It's going to be slightly different. Okay, because this one is active low. 9, if you convert to your binary, you're going to get in term of active high, you're going to get 1, 0, 0, 1. Bear in mind this is but normal binary, and normal binary are playing around with high, active high. If you are using active low, which is there is a bubble thing here, your 9 will be also low, which is convert, and all the input output here also will be converting to be 0, 1, 1, 0. So that is on your output. Please make sure you carefully look into what type of the encoder or maybe the decoder also can apply, because this all the bubble will be determined whether it is low, active low or active high. This active low, active high, not new things for you, right? So you need to take note on this. Now we have MUX and DeMUX. For MUX or multiplier and DeMUX for multipliers. Okay. Multiplier, and also the DeMUX for the demultipliers. You can see here, supposedly this is make me confused just now. This is DeMUX and this is MUX. Okay. Uh, for the multiplexer, you have last time you learned already in your module 1 about the functions. Now you look into this again, but with some of mathematical terms. When let's we go through. MUX is device that allow digital information from several sources, of course, to be routed onto a single line for transmissions over the line to common destination. So the basic multiplier has several data input line and single output. So you can see here, many to one. That is on the MUX things. For DeMUX is will be vice versa. Later we'll look into DeMUX. Okay. It also has data select input, which permit digital data on any one of the input to be switched to the output line. Select line control which input route to output. So this is the equation that you need to sometime apply in. Numbers equal to select bits log number of input log 2. MUX are also known as data collector, because you're going to collect from many to one. From many to one only. While for DeMUX, you have one sources and you're going to distribute to many. Okay, so that is the difference. That's why it's called as MUX as a data collector and DeMUX as a data distributor. Here is the flow, basically how your data going to be fit into your MUX. You have an example of the data input there and data out one only. You're going to select which one of the data that fit in to be out. So you have several data right inside and you're going to pick one of the data to be out. So you have here to the power of 1, select bit to total input. So you're going to look into the input side and what is the output. Example, when you have MUX of 1 of 2, multiplier 1 of 2, you're going to design. The design is you have S as your source, Y equal to D0. Y is going to be your output there. S will be your input side. So when S equal to 1, Y equal to D. This one is the specifications for your design. A true table is produced from the specification. So you can draw the truth table related to this truth table. So when S equal to 1, Y equal to D. Okay, where is your D? This is your D, also the input. This is your data source. From the data input, this is your output. Zero, 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 one, 0, 1, 0. This is similar things what you always do. And from here, you're going to look into the scenario that given for your MUX 1 of 2. Then that's why you will come out with this truth table. So this is from the scenario there, and that's why you can come out with your circuit. This one you can see, you can do the K-map and get the Boolean expression of your Y, and this is your circuit. Simplified version. Okay, just now you have MUX 2 of 1, 1 of 2. Now you have 1 of 4. From 4 input data here, you're going to have 1 output only. So wow, you have 5 altogether for the input side. It's quite long truth table. Is it having here? No. You can try to come out with your own with your own truth table. Let's say I give you example from, you have S1, S0, D3, D2, D1, D0, all of these 4, 5, 6, 6. And then you have Y as the output, going to have 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and the rest. So you can come out later on with the K-maps and then the Boolean expression. Lastly, you can have your logic circuit. Okay, this is your example of exercise for your encoder. Timing diagram to show the okay, you have not encoder, MUX 1 of 4 MUX multiplexer. The output will be depend on the value of the selector, which is this is your data selector. S is MSB, S1 is MSB, and S0 is LSB. The data input. Okay, so you need to determine your output. Then you're going to draw, because we don't have truth table just now, but it's okay, let's retry. 0, 0, 1, 0, 0, 0, 0, 1, 1, 0, 1. Is it correct? Where is my line? I think so. Okay, 1, 0, 0, 1, 1, 0, 0. It's too near to each other, that's why I'm quite confused. 1, 0, 0, 1, 1, 1, 1, 1, 0, 1, 0, 1, 0. Okay, from this you're going to look into, alamak, hilang tak? Tak, okay. So you need to see this one. If S0, S10, S00, this will be D0. S00, see here, and 0 here, so it's going to be D0. Then you will have 0. Okay, here will be 0. And next is we have situation of 1, 0. Let me check. 1, 0 here, it will be follow the D1. 1, 0 will D1 is 1. 0, 1, 1, 1, 1, 1, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, 0. 1, 0, 0, 1, 1, 1, 1, 0, 1, just now. Okay, 10. Okay, it is will be 10. Will be D2. D2. My D2 here is 0. Now I have 1 1 1 1. I have D3. D3 is 0. How? Okay, it's going to be 0. Next is 0 0. I'm going to have what is now D1, D0. 0 0, D0, and 1 0 will be D2. Is it D2? D3. D1. D1. Here will be 0. Okay, you can try this too. This is following the table here. So it's not too hard for you to fill in depending on the value of your selector. And this is already given on the waveform. So, is it similar to mine? Yes. Yeah. So another 2 I didn't do it. Hey. So correct. And these 2 I asked you to figure out. Okay. Next, you have exercise number 8. Maybe you can try to do it. It is also quite similar. But this thing is, similar things. Okay. Now you have DeMUX. Demultiplexer. Just now the title is very annoying me. This would be DeMUX. Multiplexer. I was like, what is this? Okay, now let's continue with our DeMUX. We have here, right here, okay, DeMUX. Just now you know already DeMUX as your data distributor. You have one source, then you going to spread it to many. So that's why you have like one source there, and going to spread to the output as a Q1, Q2, Q3, Q4, etc. So you can try to read this, and let's take a look into the example of the truth table that given there. When you have this is your input, what will be happen to your all the output, and this is the data in. Normally sometimes it's called as a EN. And from here you can have convert this table to much more compact table, and you can summarize it to be this circuit. So from there you can try to generate your own input data, what will be happen, and etc. This is basically similar to your MUX. Okay, this is our last subtopic on the code converter and also parity generator and checker. We look into first on our code converter. The purpose of this code converter circuit is to convert one type of code to another type. Example, let's say a 3 to 8 decoder convert from your binary number to one hard encoding at the output. Of course, just now you already learned. 8 to 3 encoder perform the opposite thing. Many different type of code converter circuit can be constructed. Let's say you can also have one common example, which is BCD to your 7-segment display, 7-segment decoder as explanations of your decoder sections. And that is on your code converter. And lastly, about your parity generator or checker, it is related to normally you have error. Error can occur in your digital codes being transferred from one point to another within your digital system, of course in your computer, in your system. The error take the form of undesired changes in the bit that make up the coded informations, that is 1 can change to 0, you know already, or maybe you have 0, you want to change this to be 1. When an error occur undetected, it can cause serious problem in your digital system. You're going to get like huge error later on. Basic parity logic to determine whether no of one number of 1 or 0, whether it is odd or even. Use the modulus 2 summation. Device that can do modulo 2 is XO. This is your XO example of your modulo 2. If the number of input bits is even, then your X will be 0. While if you have odd, then your X will be 1. So that is the things that you need to remember on your basic parity. It's already fixed. And parity checker, when this device is used as a parity checker, the number of input bit always be even. And when a parity error occur, the sum of even output goes low and the sum of odd output goes high. You need to understand these segments. And lastly, about your parity generator, if the device is used as an even parity generator, the parity bit is taken as some odd output. Because this output is a 0 already given, if it is an even number of input bits, it will be 1. Vice versa, of course, if there is an odd number. Okay, that is all for our module 6. I hope that you're going to go through all, and in class we're going to discuss about what we have learned. We're going to do exercise, Q&A. If you have any question, you can ask me in our class. Next, we're going to like focus on our task 2 and proceed with our module 7. Thank you for your watching. Please stay safe and have a good day. Bye bye.